Einstein made, and in principle, it's the connection that we're trying to make with extra dimensions in string theory or other ideas, is that somehow we're connecting things that seem very different by allowing this extra dimension. And it's a beautiful idea, and we just don't know if it's right, but it's a beautiful mathematical idea.
Just make a one more footnote on that. The things that we believe we're connecting by going up to the higher dimensions, we believe that all the forces of nature, not just electromagnetism and gravity, which is what Kaluza was focused upon, but we know that there are other forces of nature. Now, the strong nuclear force that's vital for keeping atoms together, the weak nuclear force responsible for things like radioactive decay. We believe in the context of string theory that gravity, electromagnetism, the strong nuclear force, the weak nuclear force, all of those are united by going to this more unified perspective of a higher dimensional setting. So it's a very beautiful picture. Doesn't mean it's right. It's a very beautiful picture.
Go ahead.
Let me pick up on that a little bit. Can we get the picture of the standard model up there? So the shadows that we see, that we're trying to interpret as evidence for new physics, maybe it's string theory or some other theory we haven't come up with yet, are these shadows. They're the shadows that your fine taxpayer dollars paid for us to discover at Fermilab and at CERN. Well, I guess that's European tax dollars.
Some of our tax dollars are there.
Some of our tax dollars are there. Okay, so you see here, this is a table of, this is the modern day periodic table of elements. Instead of, different kinds of atoms, you see here the different electrons and quarks, and they all have cousins. So you know about the electrons, you probably know about the protons, your beta protons, but for each elementary particle we know, it turns out their cousins you know much less about, because they have no apparent reason to be there. They don't play a role in chemistry, they don't form parts of your body. They're copies of the electron that are more massive that we've found, copies of the quarks that make up the proton that are more massive that we've found. This is a shadow. There's a reason that there's that structure. Why are these things repeated many times when there's no apparent need for day-to-day physics? Now, in the periodic table of elements, seeing that repeated structure eventually led people to understand that atoms are complicated composite objects. And the hope here is that this particular shadow, this complicated pattern of many different forces and many different particles, is a hint that there's a single underlying object, perhaps a string, whose different windings or oscillations can really unify this picture. Saying it's not just some, God had a bad day and decided to use 15 particles instead of 12, but really, G or E use 1, and these sorts of different.
John, do you mind if we do a little video that amplifies this?
But let me just ask one dumb question, okay?
Yeah, just one?
Just fine, yeah, I know. It's going to be a long night. One can use multidimensionality to describe this complicated and frustrating, sometimes difficult. But there's also this idea that in the sort of Higgs substrate, the sort of Higgs domain, where all these things are unified, it's at a higher energy level, or it's at a higher level of sort of other phenomena going on. And when we see these other particles, it's because the energy level, as is the case in the Big Bang, goes down and they sort of pop out in the way that ice, sort of emerges at a lower temperature than water, that sort of thing. That doesn't give prime multidimensionality for these things fleeting, right?
Absolutely not.
So
That's why string theory is one of many possible ways of interpreting this kind of shadow, and I think the shadow of the graviton, which is a little deeper and harder to interpret.
And in fact, to be fair, I mean, the string theory is sort of followed on an idea called random unification, which is really motivated actually by experiment. That the three of the forces of nature, taking gravity aside, three of the forces of nature, the strong, weak, and electromagnetic force, their strength varies with length scale. And if you extrapolate from what we see now, a very small length scale, about 15 orders of magnitude smaller than what we can measure, maybe 14 orders of magnitude smaller than what we can measure with present-day accelerators, you'll find that the strength of all those forces, which is very different on the scale we can measure now, looks the same. And that's very suggestive to people that maybe those theories do get unified and really represent different manifestations of a single force. And in some of those same theories, these families can resolve, these different shadows can result from a larger underlying symmetry group. And in that case, it doesn't result from extra dimensions.
the idea there being that it would make more sense for these forces, these particles, these shadows to have more space to work in their little sub-domain, their little dimension, that there ought to be dimensions for these shadows that we never see to have length, to have duration, to sort of have a bigger life.
Actually, can we get a picture of the Kaladi Yamail hold up here?
Well, actually, Sean, if we go, there's a direct video that we have that.
Let's do it.
Illustrates
Okay.
So